Okay, welcome everyone. This is the working group device management meeting from June 17th. We have the usual mutual introductions. If anyone is new here, I think Radoslin, perhaps you want to introduce yourself in a minute. And then we have one agenda item today about checkpoint restore for GPUs. I'm really curious whether that's how much is technically feasible and how much we can support with DRA, for example, but we'll talk about that in a minute. I can also share that we are past cap freeze. I think we got all DRA caps merged that we cared about. We retracted one, the one about cluster resource slices, cluster resource templates, because we figured that this is just a convenience functionality that can also be done otherwise with other means, and therefore we didn't pursue it further. So yeah, with cap freeze behind us, the next step, of course, is getting implementation PRs reviewed and merged, but we now have a bit more time until code freeze. But if you are working on a feature, definitely keep that in mind. We're probably going to be gated by reviewer times again. So get things ready early, and you'll increase your chance to get attention. But we'll do our best at least. Okay. Yeah, Augustine, why don't you get started with your topic and a short introduction, perhaps, because I think you've never been here before.
Hi, Patrick. Thanks so much for for the discussion and for the update. So my name is Raustin. I work on the Checkpoint Restore working group in the Kubernetes community, and we are currently exploring how to enable support for pod level checkpoint restore in Kubernetes. This is the main focus of the work that we do. I added a link to the KEP that we currently work on. But one of the things that we discussed, one of the main use cases is actually GPU workloads, and in particular, we focus on multiple use cases. One of the use cases is inference workloads, where we have, for example, inference engine like VLM, SGLang, or TensorRT-LM, and this type of workloads, they have long initialization time. So, for example, it takes about a minute or a few minutes to load the model onto the GPU, and then to essentially compute CUDA graphs, PyTorch compile, and other types of optimizations. And the way checkpointing is used is by creating a snapshot of the GPU state after the model has been initialized, and then instead of starting from scratch next time, you can essentially use this snapshot to resume. So it reduces the startup time from a few minutes to a few seconds, and it has been integrated with, for example, platforms like NVIDIA Dynamo. Um, the challenge here is we're trying to, for example, um, understand what would be the best way to enable support in Kubernetes. Um, one of the, I guess, limitations is that when you create a snapshot, it's dependent on which GPU driver you're using at the moment and which GPU device you have. For example, if you create a snapshot on H100 GPU with a specific driver version, essentially this is the same um, driver and GPU that you need to restore. And one thing we were trying to figure out is once we introduce pod level checkpoint restore, how do we, for example, um, retrieve information about about compatibility with nodes. So this is in the context of scheduling. So for example, if you want to restore you want to restore a specific snapshot and you want to identify which nodes are compatible. And we are also trying to figure out how to integrate this with DRA. So far we can checkpoint restore containers with the GPU operator, and I did some experiments with the DRA as well, but I ran into some issues. Essentially, the way checkpointing works is it saves, for example, all bind mounts. So these are, for example, the GPU libraries or the devices are mounted in the container. So during restore, it will essentially restore the mounts. But for some reason, even though the mounts were restored, the GPU didn't appear available inside the container. This is one of the issues that I ran into, and I was trying to figure out what's happening. But I'm not sure if this is enough context. Patrick, do you?
Yeah, I think it's the problem itself is clear. What the solution could be, that really depends a lot on the vendor and whether the hardware actually supports checkpoint restore. So we absolutely would need a DRA driver vendor on the call. You're working with NVIDIA GPUs. We have Alexei here who works on Intel GPUs. I don't know. I don't think we have use cases around checkpoint restore, and I don't know whether we have the capabilities to do it. I have a few questions. Are you targeting snapshotting on one node and restoring on another, or is it within the same node?
So we kind of focus on both cases. So, for example, one use case is not drain when you want to move all the workloads from the current node to the other nodes, or live migration is the other one. But also the use case with cold starts, the idea is that you create a single snapshot and then you use it many times to essentially reduce the start time.
How do you? Well, this has conceptually this has a few problems. You have data transfers that need to happen, I suppose, when you cross nodes. So there must be some way of saying, okay, well, extract some data from node A, store it somewhere, and on node B, restore it.
So this is something we are currently working on in the checkpoint restore working group. So, well, we currently focus on enabling checkpoint restore on the same node, and once this is this is changed in the core API. So we are modifying the pod spec to have a restore from field, and we're introducing a pod snapshot object that would allow us to save the checkpoints. But once this is kind of the foundation for the next step. The next step will be live migration, which is this transfer mechanism that you mentioned.
Regarding taking a snapshot of a GPU, I could imagine that you would need to work with a DRA driver and tell it to create a snapshot, whatever that snapshot looks like, a stream of bytes and some metadata then. And metadata could include things like device selectors, and that could encode something like, okay, this snapshot is suitable for a device where the driver version is exactly this one here. This could be exposed to the scheduler as metadata when you have a resource claim with a restore from field, something like that. That could become part of a Kubernetes API where the driver supplied snapshot metadata gets exposed to the scheduler in a way that allows it to choose a compatible device on some node. But Kubernetes doesn't know. Kubernetes doesn't know what the criteria are. This has to come from the DRA driver, which knows about driver versions, hardware limitations. Maybe a snapshot can be restored on a device with a different memory size. Maybe not. It certainly will depend on the hardware capabilities. So the DRA driver would be the starting point. And then the scheduler obviously needs to know that there is a restore going on. So what you just mentioned about the pod spec with restore from, I guess we can add something like that in a resource claim in the request for a device where we say we want a device that can restore this. And yeah, then maybe we may also need some metadata. Or well, actually, if we make it abstract and just say restore from has cell selectors attached to it, then this will clearly only when a DRA driver vendor can make sure that this is targeting devices that actually support the snapshot. Well, I think that could be covered. In terms of APIs, how do you decide when to take a snapshot? Is that a manual operation, or is it triggered by a certain state transition, like init containers complete or something like that?
So this actually depends on the application, the use case and the application. So with inference workloads, is the approach that we currently use. They have sort of like HTTP endpoint that tells you when the model is ready, essentially when the model has been loaded and initialized. And what we do is we just wait for this endpoint to become available, and then we can create a snapshot. So this means that after restore, the inference engine will be ready to serve requests. But we have other use cases like fault tolerance, for example, for training workloads. So in this case, we would have periodic checkpoints. So for example, every half an hour we create checkpoints. So if something fails, we can essentially recover the workload from the last checkpoint. And there are other use cases as well, like forensic analysis, where when we detect, for example, cyber attack, what we do is we start creating checkpoints very frequently so that we can capture the state of the container and preserve this as evidence. So, for example, the problem is if the attacker exits the container, everything that has been inside, like the processes and the state, disappears. So the idea of snapshots for this use case is to preserve this as evidence. So yeah, we have a few different use cases, but essentially when we create the checkpoint depends on the application and the use case.
Yeah. Okay. Yeah.
I want to point out that we have something called the NICO, so essentially multi-GPU and multi-node checkpoints as well. And yeah.
Okay. I was trying to ask whether this checkpointing is triggered from kubelet. Is it kubelet managing that, or is it an external component on the node?
Yeah, so the idea is, so what Kubernetes supports today is a kubelet API called Container Checkpoint. So you can, you have this a kubelet Waco API. So it's intentionally restricted to Waco nodes so that we can essentially identify. One of the challenges is the checkpoint contains a full snapshot of the memory state. So this includes all secrets and sensitive data. So we don't want to expose this, and that's why the initial implementation was limited to essentially kubelet API. And what we're currently implementing with pod level checkpoint restore is essentially kubelet CRI APIs that allow the container runtime to essentially create a snapshot checkpoint restore, but also the essentially pod snapshot object, that pod checkpoint object that allows you to essentially request for checkpoint to be created, and then essentially we modify both the kubelet, the API server, and the container runtime to implement this.
Yeah. Okay. That's good, because the kubelet is also the one which has a gRPC connection to all DRA drivers that are relevant for a pod that is running. I'm thinking specifically of the device health API implementation. And you could do something similar where you say, okay, well, we want kubelet to take a snapshot at the devices allocated for that pod. We figure out which DRA drivers are responsible for it. And that's exactly the same logic that we have for the device health, where device health gets posted to the pod status by querying the responsible DRA drivers. And you could do something similar and create a gRPC interface where you, well, first of all, during registration, figure out whether the DRA driver actually has that gRPC interface implemented. And then if it does, you can ask it to take a snapshot of a certain device. And you can tell it, I don't know, probably to write the snapshot to a local file where Kubelet then can do something with it to move the data or make it available for a restore operation.
So I guess it will the way the checkpointing mechanism is currently implemented. So this part of the GPU driver, it's implemented for both in the Linux kernel for AMD GPUs and in the CUDA driver for NVIDIA GPUs. For NVIDIA, it works slightly different in both cases, but for NVIDIA GPUs, the way it works is when you create a snapshot, a checkpoint, what it does, it moves the GPU state into host memory. So essentially, the GPU state is part of the application address space, and when we checkpoint the container in the pod, so this is kind of included in the checkpoint.
Okay, well, where the data lands is something we need to figure it out. But yeah, if that's, I can imagine there might be different mechanisms. So the gRPC interface between Kubelet and the DRA driver would need to be a bit more flexible. Maybe it all depends on what hardware vendors can support, what they want to support. But ultimately, I think it's the same approach. The gRPC interface says take a snapshot, and then you get some result back, and that result can also include the metadata that I described that needs to be exposed to the scheduler when you want to restore. In terms of, yeah.
I want to also ask one question about essentially distributed workloads when we have, for example, NVLink and essentially NICO communication. So the way NVIDIA currently, so this is something that NVIDIA are currently introducing in the next release for NICO, and the way this is implemented is with essentially shim. So essentially a shared library that is preloaded for the application, and what it does, it allows you to essentially tear down and then rebuild the essentially NICO communications. I'm currently trying to figure out what would be the best way of integrating this with Kubernetes and with the GPU operator, the DRA driver. Do you have any advice on that?
No, there's combinations of devices that then gets increasingly harder. So no, that probably would need to go into a design document that explains the use cases. Then we need someone from NVIDIA to tell us how that could work. And yeah, that needs further discussion. Even the rough outline of a potential solution that I just described, that is something that someone would need to prototype, explore, describe in more detail. And then we need to get some hardware vendor on board who wants to support that with their hardware. Well, with NVIDIA, the DRA driver now is owned by Kubernetes, but you would still need to work with the maintainers because they would have to review PRs and then make a decision whether that's actually something that they can merge or want to merge, or whether it'll just remain in a fork of a driver until it's ready according to some criteria. But at least the source code is available for prototyping. So that would be something, but it depends also on how much you want to do the implementation yourself or can, or whether you want someone from NVIDIA or some other community member to work with you on that.
I mean, we collaborate with a team at NVIDIA that works on the checkpoint functionality. So, for example, I have meetings with them to discuss what they're currently working on. And, I'm a maintainer of the checkpoint restore in user space, the Creo project. So this is essentially the tool that we use to create checkpoints, and we implemented a plugin that essentially interacts with the GPU driver. And this is how
okay.
Yeah.
So sounds like you're already talking to the right people. So the Kubernetes API side then is missing, but I think if you want to move forward, a draft KEP in a Google Doc may be a good first step. But we need to get other people on this and have some proposal of how the flow could work, and then we can figure out what the gRPC interface could look like, what the Kubernetes API could look like. But seems doable, at least to me.
Yeah. I mean, we had a presentation at KubeCon last year when we essentially showed that this could be done, and we are trying to move forward. But we were also discussing in the Checkpoint Restore working group as a next step to work on a KEP for GPU, essentially to enable support for GPU snapshots, GPU Checkpoint Restore, and that's why I want to come here to discuss it.
Yeah. But it's good to give us a heads up. A Google Doc, I think, is a bit easier to work with collaboratively. That's why I suggested it instead of going straight to writing a KEP in Markdown and creating a PR. For the early stages, GitHub is not a good place to make rapid changes to a doc. That's the review process of review user interface in GitHub just isn't good for that. But it's I don't know who would be reviewing it. Well, I'm interested, but I don't have a stake in it. So priority for me would be a bit low, but we can see. You also need to be aware that this is the, Europe-Asia time zone meeting. We have a lot more participants in the Tuesday meetings, the one that takes place next Tuesday, for example. So if you want to get other people involved, it may be worthwhile to bring it up again there if you can make the time.
Okay. Thank you, Patrick. I think this is very helpful. I'll try to, I'll discuss this in the Checkpoint Restore working group, and we can try to create a document that describes the use cases and essentially to help us with discussing this.
Yep. Okay. Yeah, the purpose of this meeting really was to have a discussion place for people who can't make the later the day US Europe time zone. So we have people like Bang, who's in Japan, and that other meeting just isn't friendly for people in Asia. It's basically middle of the night, so it's very unreasonable to expect that they show up there if they have something to discuss. So with that said, Bang, do you have anything? Anyone else wants to discuss something today? I have one topic, and that's scheduler performance. Just a slight update. I think we talked about that already. So we have merged the consumable capacity scheduler perf update. It's currently running, and we should have some data in PerfDash. But I also want to point out that Gita's PR or Gita's improvement of scheduling performance is coming, I hope, fairly soon. So my current thinking is that we get at least that one in before we update performance thresholds, because then we only need to do it once. It's also an interesting problem that we are currently not solving with our scheduler perf thresholds. We get a test failure in the periodic job if performance regresses or falls below the threshold. But if an old threshold was chosen before some optimization, it basically remains too low. So we also need to increase the thresholds after we did some performance improvement. And we currently don't have a mechanism to detect that. So my current thinking is that we also need to fail the scheduler perf job if the threshold is way below the currently observed performance. And that's currently missing. And if I add it now, we will have lots of failures because I think some of our performance data is actually better than we thought. So yeah, let's continue reviewing scheduler perf benchmarks. I think now that we have something reasonable for consumable capacity, we need to do the same for partitionable devices, because that also uses odd setups and could be improved. And then we do the performance optimization from Gita. I have another one pending. It works locally for me, that I'll probably submit for review when Gitas is in. Maybe also the other way around. I haven't quite figured that out yet. I might just currently I'm basing my work on hers, but I can also try it without, and then we have two independent PRs that both improve performance. So once all of that is done, then we can revisit the thresholds and make them meet the current performance of the upcoming 137.
Patrick, when you say the threshold, you mean like the thresholds of the main config of the DRA perf, right? Or is this like for each feature as well?
It's probably for all features, because also Gita's improvement is around handling of resource claim events. Currently, it might not change. Well, it affects benchmarks that create a large number of pods where each pod uses a resource claim template. What happens is, with this thundering herd problem, the scheduler gets lots of update notifications for resource claims, and it has to match those against all the pods that are currently unschedulable because they are waiting for their resource claims to be created. And what Gita observed is that this basically creates an n squared problem where just event handling and checking pods over and over again takes up quite a bit of CPU time in the scheduler. And the optimization that she's proposing is to inform the scheduler from the DRA plugin that this resource claim update only is relevant for a few pods, ideally, typically only one, and then only that pod gets checked whether it's now schedulable.
Mm-hmm.
And that's a really nice performance improvement for this case where a workload immediately creates thousands of pods. You don't see it with only a handful of pods, but with once you get into the order of 100 or 1,000, it becomes noticeable. And the non-steady workloads that we have with scheduler perf, they do exactly that. They create a large number of pods, sometimes with dedicated resource claims created manually, sometimes with resource claim templates. It depends a bit.
Mm-hmm.
But the ones that create resource claim templates, they definitely benefit from this optimization.
I see. Okay. Yeah, I mean, like, what I noticed is like the parameter that we add for like what is that, the max pod or matrix subsub is affect the result of the throughput. I mean, yeah, when we put it like 10 pods, the result is about like 20, 30. But if like I increase to 100 or 200 or like thousands, it can go for the 100 pod per second.
Is that for the steady state?
Yeah, I
Yeah.
wonder what
Yeah.
is that expected behavior in that case? I don't know.
Yeah, I looked. That's what I looked into myself again, and I have a change for that steady state test load generator. My thinking originally was that it simulates a workload where pods get a handful, 10 basically. 10 pods get created together in a certain cluster state. The scheduler schedules them, the workload observes that these are done, they get deleted, and the next batch gets created. That's the current implementation. Basically, it creates batches of pods. But what I found also is that this creates downtime for the scheduler. It actually isn't running 100% in scheduling mode, because there is this time where it has done its work. Now the workload, the test load generator needs to do something, and that affects throughput.
Yeah.
What I have pending locally is a change where the scheduler perf load generator creates 10 pods and then waits for scheduled pods. And as soon as a pod gets scheduled, it creates the next one. Basically, it continuously creates pods. And that also increased the throughput. It's a different scenario, but I think it's better for actual performance analysis, because it keeps the scheduler busy, and that's the main goal of scheduler perf, that we are clearly seeing a limitation by the scheduler performance and not just something else like the delays caused by the test itself.
I see. Yeah, I agree that is might be need the considerations, because like currently the throughput is too different between like using the steady and not using it, and also like having the batch or not the batch. So
yeah, well, the performance is definitely going to be different when we create a large number of pods. We don't have the delays, but we also don't get consistent throughput. So this gnuplot diagram, the dot files that are dumped into the test directory, they show throughput over time instead of just the average throughput or the percentiles. And what I observed is that with large numbers of pods created initially, the throughput varies quite a lot over the runtime of the test.
yes, yeah, I also observe the same as well.
Yeah, and I mean that's what's happening, but it's basically a different use case. We are benchmarking different use cases, and we hope to make optimizations that benefit all of them. Or perhaps we, like Gita, we are trying to particularly optimize the case with large numbers of pods created at once. So I think both types of benchmarks make sense, but they are not comparable. This is basically apples and oranges.
Yeah, like, so my next question would be like, if we think both is important, like for each feature we need both, or like we need just only one of it.
I think I don't know. Probably both. And then we have both types of benchmarks to base our optimization efforts on. Having expectations for the performance, that comes pretty much from, well, how quickly is it to schedule pods without advanced features compared to doing the same with some feature like consumable capacity. Of course, it won't be the same because it does more work, but are we at least still in the same ballpark? That's, I think, the question.
Yeah, that makes sense. Okay. Yeah, it's just been that I also have to update it this case for the other one as well. I think I have to solely the steady one.
Sorry, say that again?
Oh, sorry. Like, does that mean like I have to update the test case again as well to have the one that is not steady state?
Did you drop that one? I thought we still had it, but I don't remember.
With the performance, I think I set or to the steady to true for all the cases.
Okay, so the performer for perf-dash we only do the steady state. Well, it's a good start. I wouldn't worry too much right now. I think we can revisit that when we have all the performance improvements in place, and then do a consistency check across our different features, and then we can update it.
Okay, thank you so much. Yeah, thank you.
And we may also want to consolidate a little bit how we define this test. You did one thing that I actually liked. You had the steady state as a parameter, so you could have the same operation with lots of nodes, lots of pods, and not steady state, and just have a different use case where it's using the steady state. I think that may be actually a good sort of consolidation also for the main DRA performance config, but yeah, it's a bit more concise. And also the create a deploy DRA driver, I think what we found that we can template the resource slices. That wasn't something that was possible initially. That led to the creation of that whole separate create a deploy DRA driver step. We may just deprecate that and remove it because we have a better mechanism now.
Okay. Thank you.
Okay. Anything else? If not, then thanks for joining. Francesco, I have one ongoing topic perhaps, but that's, well, I can mention it here, about DRA E2E node testing. I've been working towards splitting up our DRA E2E node tests so that each job only tests one machine and runtime combination. We have some jobs where we run, I think it's containerd, we run with 2 operating systems in the same job. And that creates more work in pre-submits because we don't basically create 2 virtual machines where one might be enough. I now have all the technical bits and pieces coming together, but I need some PRs merged. I made that agenda for the Node CI meeting that I think is happening today.
Yes, it is.
Yeah, so I put something on the agenda. We can discuss it more.
Absolutely. Absolutely.
Yeah. So that's just an early heads up.
No problem. Thank you for that.
Yeah. Okay. Then that really was all. Nothing else, I hope, or I think comes to mind. So thanks, and see you again in 2 weeks. Goodbye.
Thank you.
Thank you. Thank you.